Okay, hi everyone. Welcome to our 76th session of MedAI. Before I formally introduce our speaker today, I would like to announce that Amara from Mayo Clinic will take over my role as a co-organizer of MedAI because I have graduated from Stanford. Amara is a senior data science analyst in machine learning intelligence in medicine and imaging lab at Mayo Clinic, Arizona. She received her PhD degree in computer science from University of Central Florida, where her work was focused on confluence of image and natural language processing for semantic understanding of multimodal datasets. She received her postdoc training at Emory University and Mayo Clinic, Arizona, where her research interests shifted to development of fusion models for multimodal medical data for applications including clinical event prediction and opportunistic screening for diseases. Her research has been published in reputable journals, including IEEE TPAMI, Journal of American Medical Informatics Association, Nature Digital Medicine, and IEEE Journal of Biomedical and Health Informatics. So let's welcome Amara to the team. Today, we have Yasha from Harvard with us to present his research on multimodal learning with graphs for biomedical applications. Yasha is a PhD candidate in the Bioinformatics and Integrative Genomics program at Harvard Medical School, co-advised by Marika Zinnik and Maha Fahad. With publications in Nature Machine Intelligence, Nature Breast Cancer, and Lancet Micro, he is interested in designing the next generation of machine learning methods to predict genotypes from genotypes. Specifically, he is interested in understanding and improving the ability of these models to generalize to new and unseen genotypes. Before Harvard, he received a BS in EECS and bioengineering at UC Berkeley. He did his research on designing computational methods to understand bacterial communities. Thank you, Yasha, for joining us today. Before we start, could you tell us when you want to take questions?
Thanks for having me here. I can take questions whenever through the presentation. Just start talking and I'll stop.
Okay, sounds good. So let's try to make this session as interactive as possible. Without further ado, let me hand it over to Yasha.
Yeah, well, thanks everyone for coming today, and thank you for this invitation. I'll be presenting the work in a perspective that was recently published in Nature Machine Intelligence a few days ago. It's up there, you can see it. Due to this being a more general audience, specifically interested in medical AI, I'll be focusing on the part of the perspective where we talk about the applications of what we talk about multimodal learning of graphs for biomedical applications, and specifically how people hopefully in the call can use multimodal learning with graphs in their own applications. So yeah, with further ado, I'll start. So as most of us probably on this call know, especially like GPT-4 and this idea of multimodal learning being a large buzzword being thrown around right now, multimodal learning studies how heterogeneous and complex descriptors can be optimized to create a robust generalized learning system. So in biomedical AI right now, there is recently a paper published in Nature, a perspective published in Nature only a few days ago, talking about how these generalized medical intelligence models can be trained by integrating many different sort of data modalities or data types. For example, I used to do work in histopathology slides where you have like a picture of a slide of a breast cancer tissue, and you tried to train a convolutional neural net to predict whether someone had breast cancer or not. So that's like the images part. But now what people are doing, they're combining not only this imaging modality, they're combining this imaging modality with this omics modality here about the actual genomic information about the patient, about the tumor, to use this to improve predictive capabilities. So this idea of combining different sort of data modalities is increasingly popular in medical AI and is an important factor moving forward. But there are challenges that exist in multimodal learning. Two of the main challenges that I identify early on in the paper is one known as modality collapse. So what happens is that, for example, in the histopathology slide, we may have an image of a patient's breast cancer tissue and also their genomic information. the model may just decide to focus on the image and not take any information from the genomics because it's just easier to do so and it's able to get decent performance on most examples. And as a result, it's not actually leveraging the capabilities of multimodality, because the whole idea of multimodal learning is that the weakness of one modality can potentially be the strength of the other. And so when modality collapse happens, we miss out on that advantage. And the next challenge is this idea of missing modalities. As you can imagine, getting the genomic information about a person is not easy, and some people that may not have that information. So how do we handle this missing modality problem? And the insight that led us to be interested in graph learning as like a topic to be interested in is that different modalities often have intricate relational dependencies between them that we can leverage by building these optimally defined graphs. So there may be relationships in between like an image or your genomic information or an EHR data. And in leveraging this relational information, we can better hopefully overcome these challenges and actually do multimodal learning. And so using this idea of graph learning in addition to multimodal, or applying graphs in areas where traditionally we don't expect graphs to be used, this is called multimodal graph learning, and that's the focus of this perspective. So I'm not sure what people's like backgrounds are with graph neural networks, so I'll do a very, very brief introduction to graph neural networks. So a graph neural network is a type of machine learning model that learns a representation of an input graph. And these representations of the input graphs reflects the structure of the graph. So for example, in this node here, if we learn some representation with a graph neural network, we'll learn a representation of this node that encodes information about its relative structure in this graph. So just how in an image, we learn a representation of an image that represents the sort of features that are inside this image, like if there's like a dog or a cat or something like that. In a graph neural network, we learn features that represent the actual structure of this graph. And the way a graph neural network is able to do this is that for a given node, so let's say this node, we perform something called message passing. So it looks at its neighbors and it takes the representations of its neighbors and its current representation, adds them up together, and uses this to update its own representation. So why it's called message passing is because your neighbors are sort of passing messages to you and you use this to update yourself. So in a very basic sense, this is what a graph neural network does. And throughout the field, there are many variants of this baseline design of a graph neural network to encode different sort of inductive biases that are relevant to your applications. And we'll talk about more of those later on. So what we did is we went out and we read around 140 or so different papers from many different applications, ranging from images, language, physics, chemistry, and biology. And as we were reading these papers, we wanted to see how they use graph learning in their non-traditional applications. And we realized that there is a consistency across all these different applications and how graphs are being used. There's a very predictable pattern to it. And we realized that there's an emerging field here that we call multimodal graph learning. This idea of using these graph neural networks I talked about earlier in these diverse and different applications. But although they are very diverse, these applications, they all follow a similar sort of blueprint. And this is what we introduced in the paper called a multimodal graph learning blueprint. And the idea is that by introducing and identifying this blueprint, and then going through all these applications and showing how they fall under this blueprint, this can serve as a roadmap to anyone who's interested in using graph learning for their non-standard applications moving forward, because they can look at what other people have done in the past and organize their thinking when approaching this problem. So I'll go over this blueprint briefly, as we'll talk about it more throughout this talk. There are four main components of this blueprint. So let's say, for example, we have an image, right? So we have an image and we decided, okay, we want to use graph learning for this image. Why would you want to use graph learning for this image? Because often in an image, for many tasks, the dependencies against the different objects in the image to each other can be like a long-range dependency that's not as easily captured in like a convolutional neural network. And so you can hard code these dependencies between these objects in a graph neural network, and then you can learn on these interdependencies between these objects and then use this to perform better on your task. So if we want to apply graph learning to this image, the first step of our component is identifying entities. So the question is, this graph that you're going to construct, this multimodal graph, what are these entities going to actually represent? So in the case of images, what I've seen is that there's two main approaches to this. One is this idea of superpixels, where you just take large chunks of the image and you define it into one node and have this node represent a chunk of an image. And the representation, the initial representation of this node is initialized based on some featureization of the specific superpixel. Or you could have it, you can run like some segmentation algorithm or segmentation, other convolutional neural network on this image to identify the objects in the image. And every node then represents the object. And this is the initial graph that you have. So this first component, identifying entities, is really based on your specific application of interest. Because if you're interested in perhaps image classification, you may want to go in this superpixel route. But if you're interested in understanding object-to-object relationships in an image, you may want to have every node represent this like segmented, this segmentation, pre-segmented image. And then once you have the nodes, the next step is called uncovering topology. So how can we connect these nodes together in this multimodal graph? And so in the image example, if you have superpixels, what people do is they connect two superpixels that are spatially adjacent to each other with an edge, or they connect each superpixel to its k nearest neighbors. If your nodes represent actual objects in an image, usually what is done is that you'll have two separate graphs. One graph that represents all interactions between human objects in an image, so like a hand, a face, a foot, and another graph that represents all the objects in an image, and then you'll have interrelationships between these two graphs. And that's in order to reason over these long-range interactions between objects in an image. And so after you have this, you have a learned graph with multimodal attributes. So you constructed your graph, and then this whole section here is called the structural learning section. And then the third component is this idea of propagating information. How can we actually learn on this graph? Learn node representations that can then be useful for our downstream task. And so what most people do is, like, initially you'll use just a vanilla graph neural network, as I described. You'll use a graph neural network, you'll get your node representations, and then you'll use that for your task. But what you can do is you can modify the vanilla graph neural network algorithm to encode inductive biases that are relevant for your particular task. For example, in images, it's not only what is relevant is not only the objects and their proximity to each other, but the direction of the objects with respect to each other. For example, if I'm trying to understand human object relationships in an image, if a person is facing a surfboard or if a surfboard is far away from a person, that gives information as to whether or not they may be interacting with that object. So what you would do is you would perhaps, what some papers have done is they've modified this vanilla graph neural network, where now it includes these edge representations. Every edge now has a representation that encodes some idea of directionality. And when you do message passing, you don't only get the neighbors representations, but you also include the edge representations to reason over this directionality. And so this modification of like a standard graph neural network to encode an inductive bias that's relative to your problem is what we call the third component, propagating information. And then the last one is something called mixing representations. So the idea, we're not trying to say like, oh, a graph neural network this is like the final thing. Everyone should use this. No one should use anything else. And these alternative applications, there are already existing models that do quite well, or may already have a decent performance. So what the question is, how do we use this graph neural network, these node representations, in conjunction with other sort of models that may exist? And so you can have like a multi-channel model where you take like the output of a graph neural network, and in an image, you take an output of a convolutional neural network, and then you somehow merge those representations or mix those representations together before getting like a final result that you use for your downstream predictions. And so the question of how you integrate this graph learning component into this greater model that you're building, that's this mixing representations part. And you'll see examples of this as we go on. And so all of this is a multimodal graph learning blueprint. And this perspective, we go through these applications and we explain how different sort of applications have instantiated these components.
May I ask a question here?
Yeah.
Yeah, so I guess in these blueprints, the nodes are basically different data modalities, right?
Yes, so nodes can either be different data modalities, but they can also, as you see here, like different data modalities can go into like a single node. They're basically what is the the fundamental unit that we are interested in reasoning over in your input. So I'll give like a biomedical application, which I'll go over. So for example, like a small molecule, the fundamental unit we're interested in is an atom, perhaps, or a group of atoms. And then what's the actual node representation is, we may instantiate that representation of the atom with quantum mechanical features or other sort of data modalities to represent this atom. So yeah.
You guys want this space?
Sorry.
I think we just got some interference.
Okay, no worries.
Sorry. So a follow-up question is, so let's say the node, like some nodes are from different modalities. So is this graph usually considered as like a heterogeneous graph?
Yes. It's up to you how you define your graph. It could definitely be a heterogeneous graph. I think the way that we've formulated this blueprint, the entities that you defined are like homogeneous, like every node represents the same thing, like the same entity. So like it's not like one node will be an atom, another node will be a molecule. But yeah, but you can have like different data modalities pouring into different nodes, as long as those nodes represent the same fundamental unit that we're interested in reasoning over.
I see. Got it. Thanks.
I had a quick follow-up question as well. Oh, sorry, Amara, do you want to go first?
No, I actually just wanted to clarify on this C's point as well, because when you say data modality and you're pointing to this one node, it feels like all of the nodes are coming from different modalities, right? But you call it multimodal because multiple modalities might be going into the same node, right? And
Yes.
then you have the same, let's say, 3 modalities available for your node 1, 2, and 3, or 4 and 5, right? And so each node contains multiple modalities. That's why in your notation, it's mixed representation or multimodal graph.
Yes, that's correct. And it's also, that's one way that this is multimodal. And another way is just the idea that we're adding this graph learning with plus something else. So in this case, if we're reasoning over images, it'd be images plus graphs. So this is also, it's also multimodal in that sense.
Okay. So you're taking it basically 2 sources of information. So you have individual information coming from the image itself, and then from its connection to other images, you would take that information as another modality, right?
Yes.
Okay, makes sense.
Okay. Yeah, I think there's another question.
Yeah, I think I'm just curious about, like, is the blueprint supposed to be something that you like? Let's say you have image text pairs. So for instance, you have a caption and you have an image. Do you how does the graph look like if you have such an example, or maybe in the biomedical space, if you have like a time series associated with an image, like how would you use this blueprint to kind of figure out what the nodes should be?
Yeah, so I've seen examples of like image with like a caption. So what you do, you'd have like a visual image, a visual graph. So one graph that represents the features in your image. So like a person or something and their spatial relationship with each other. And then another graph that represents the text itself, the caption, and you create like a semantic graph. So each node represents a word and there's connections based on the semantics, like, oh, what follows what relates to what. And then you would have cross, and so that'd be like you're identifying your entities. And then the topology, there'd be each individual graph, and then there'd be like cross graph interactions. So perhaps you would add like an edge between, like, if an image talks about a dog, if the caption talks about a dog, and you know one of these objects you identified as a dog, there's like an edge between like between the 2 different graphs that represent the dog in the image and the dog in the text. And then propagating information, you'd probably have like so like just like an image propagation, a text propagation, and then a cross propagation step. And you'd have different parameters. You would have different weight parameters for each one of those steps. And then you would mix those representations together for the final one. You just like average the node representations. And that's what I've seen for like visual text reasoning applications. That's how they do it.
Oh, okay.
And they all some one of the studies that we looked at, actually, if there was also a number in the caption, they have like this math graph where every node represents like a number and the relationship between them. And then so they have these like 3 levels of graphs, and they use this to reason within every sort of like domain here, within the image, within the language, within this math, and then they cross that information, then use it for the final output. But I think it will become more clear as I dive into specific biomedical applications.
Okay, sounds good. Thank you.
Yeah. But yeah, the last thing is this blueprint, like it's just meant to be like a conceptual framework to organize all these existing works, and then allow other people who are interested in who are to do this sort of work for their applications. But I'll talk about specifically 2 examples. One of them is multimodal graph learning for small molecule modeling. So usually in small molecule modeling, we have some sort of molecule here with like features like polarity and stuff like that. And we want to try to predict the tasks in this space, or trying to predict the property of a molecule. So this is for drug discovery, like we want to predict the solubility of a small molecule, a potential drug. We want to predict its dose response curve, something like that. Or if we have 2 molecules, we maybe want to predict whether they will react or not with each other, and in what way they'll react. And in these sort of applications, multimodal graph learning, this blueprint has been used. So the first question is, how do we construct a graph from this molecule? And as I talked about earlier, this is an example of the first 2 components of this. We identify an entity. So in this case, it's an atom. And representations are of these nodes that represent atoms are like your atomic number, the valence, etc. And then the bonds here represent, then the edges here have representations themselves that represent like the type of bond. So whether it's like a double bond or single bond. And usually in this space, they use something called RDKit, which is a common computational tool to quickly featureize these atoms and get relevant chemical features that they then use to initialize these representations. So now that we have this representation for the small molecule, then you just run like a standard like graph neural network. That's your propagating information step. And then you average all the representations of these atoms, and then you call this your small molecule representation. Now, this may sound very simple to like a lot of you on this call, but doing this actually gets you a lot of mileage. There is a study in Cell that was a deep learning approach to antibiotic discovery that used this sort of architecture, and they were able to identify a novel antibiotic. And the way they did this is they had a data set where they given a small molecule, they know it has this level of inhibition in E. coli to inhibit the growth of E. coli. And they trained this model to, given the structure of this small molecule, predict whether it'll inhibit E. coli growth or not. And then they screened a large library of compounds, and they found a novel antibiotic that people hadn't considered before. And they were able to do this with this simple model. And there's other papers out there like this one. This paper talks about reaction properties. So as I talked about earlier, given 2 molecules, can we predict whether they will react or not, and in what way they'll react? And the model that they used to do that was actually based on this simple representation of a small molecule and a simple graph neural network. But there are new studies that are recently coming out that modify this message passing to include inductive biases that are relevant to small molecules. So I'll highlight this work that came out, I think, a year or 2 ago, which basically the idea is that these small molecules have something called chirality, where the relative spatial relationship of these atoms to each other. So if they're like if the molecule is like a mirror image of itself, it can have completely different properties. And we've all heard this in our chemistry courses. But the problem is that standard message passing is invariant to any sort of like translation of this graph. But we don't want it to be, because if you flip the graph in some way, it's going to have a different sort of, it should have a different representation. It should have a different prediction. And so what this group did is they use a similar setup as I talked about before, but instead of doing standard message passing, they do a they take every permutation of the atoms that correspond to a chiral group or a group of rotations, such that these group of rotations across the center should yield a representation that should yield a single representation, should not change depending on the rotation. And they were able, I won't go into the details, but they modified the message passing to look over these permutations of these atoms that are within this chiral group. And in this way, they were able to create a representation of the molecule that was specific to the chirality and was able to improve this performance. So in this way, you can see that they've modified the standard graph neural network, and they've modified the standard graph neural network in a way that they can introduce inductive biases that are relevant for this particular task. And another example in the last component, the mixing representations, this is another paper that's this model is used widely. But what they do here is they use a standard graph neural network here. This called MPNN is a message passing neural network. And they get the features of the atoms here, but they also incorporate these quantum mechanical bond features. So in an understanding and predicting like the properties of a small molecule, there exists a large body of work that uses quantum mechanics and quantum mechanical based algorithms to define the set of features that should be relevant for prediction. And these features are not specific to any particular bond, but are just about the whole molecule itself. So instead of just using this graph neural network and its representations of the small molecule, they also bring in this quantum mechanical descriptor from these other algorithms, and they concatenate these features together, and then they use this to get the solution. And this is an example of it's a very simple example, but it's an example of mixing representations, bringing in the graph neural network portion, the multimodal graph learning, getting those representations, and then mixing it with some existing external model to do your task. And the last example in the small molecules that I'll bring up is this idea here. So as I talked about, we're interested in predicting whether one small molecule will interact with another small molecule, and in what way will they interact. So what this paper did is that they had the graph representations of these two small molecules, and then in addition to the message passing, so they would do one round of message passing within a small molecule, and then they had global attention of every atom in one small molecule to every other atom in another small molecule. And this global attention, and by having this attention, the model could learn which atoms potentially interact with which other atoms in this other small molecule. And in this way, it can learn how the reaction actually occurs between these two small molecules. And this is an example of, again, changing the message passing of a graph neural network to encode an inductive bias. And the inductive bias in this case is that there's these interactions between these atoms, between these two molecules, and the interaction is important for the predictive task, and the model needs to figure that out. And so that's an example of modifying the third component, propagating information. And so that was an example of multimodal graph learning for small molecule design, but now I'll talk about an example for protein design. So here we have a protein, and a protein is a multi-scale biological entity. On one hand, you have the simple amino acid sequence that defines a protein, and then that amino acid folds onto itself to form a secondary structure, and then based on that secondary structure, then you have a surface manifold of this protein itself. So there's three different representations of a protein. There's multiple sort of biological contexts, and each one is important for a predictive task. So this makes it prime for this idea of multimodal graph learning. Because in here, where you identify the entities, these entities can either be the underlying amino acids, a sequence of a protein, or it could be this idea of having a molecular superpixel here. So you have a node that represents an amino acid, but then you also have a node that represents the surface of the protein. And the idea is that different amino acids in their interaction create the surface manifold of this protein. And it's not only the identity of the amino acid that is important, but it's also the shape of this surface manifold, because it's ultimately linked in the structure of the protein and how it will interact with other proteins or a small molecule. And identifying this amino acid and this surface is this is an example of identifying entities, and connecting them in this way is an example of uncovering topology. And what I just showed to you, this idea of having a graph for the amino acid, this molecular superpixel that summarizes a chunk of this surface of this protein, and then connecting the amino acid to the superpixel in this way. Constructing the graph in this way is from this paper that was released fairly recently, and is an example of and then what they had is not only did they construct this multimodal graph, but they also revised this message passing. So similar to what I described earlier, they had one round of message passing to understand the structure of the amino acids themselves, one round of message passing to understand these molecular superpixels, the surface, and surface-to-surface relationships, and then one round of message passing to send messages back in between, back and forth. And by modifying a strandograph neural net where you would have everything just connected and not have these different rounds of message passing, they're able to incorporate these inductive biases that both these the relationships within and across these different scales of hierarchical scales in a protein are important, and they're able to get a better performance. But you may ask yourself, like, in the molecule sense, it was very clear, like we would have an atom, right? Like what else would we do other than an atom? Or in the protein sense, it's very obvious, it'd be like amino acid or this molecular superpixel. What else could we potentially, how else could we do this topology? There are a lot of variants in this field. This paper came out like this year, and what it does is that instead of a protein being represented, they take in the way I talked about previously. Here, what they do is they take the three-dimensional structure of a protein, and they define every node again as an amino acid, but they connect nodes to each other based on their position in this three-dimensional space. So given the three-dimensional structure of a protein, given amino acid, we define a sphere of a certain angstrom radius, and then we connect every node to every one of these amino acid within this radius. And then we also have edges depending on the sequence. And we also have this idea of a k nearest neighbor edge where you connect to the k nearest neighbors within a certain angstrom length. And by constructing this protein graph in this way, in the previous example where you're talking about the surface of the protein, you're incorporating information about the surface manifold. But here you're doing specifically about the protein three-dimensional structure. And so these are two different ways of uncovering topology or doing the second component for protein representation learning. And they're both valid, but they're just different ways of approachment. There's a lot of variation one can have for this component. And another one I'll bring is this other paper from 2020, where they discard this idea of looking at the underlying what is the amino acid sequence, and instead just focus on the surface manifold themselves. And what they do is they define a point on the surface manifold, and this a geodesic sort of they define this circle on the surface manifold, and every node represents one of these circles, and they're connected based on their proximity to each other. And so this is a different example of uncovering topology. And each one is sort of used for different tasks. The authors argue that this sort of representation of the graph, and then using as a standard graph neural network, will give you better performance for protein-protein interaction learning. But for the previous approach, where it's for the previous approach, it's less focused on protein-protein interactions, but more focused on predicting the actual properties of a specific protein itself. So depending on the downstream tasks you're interested in, you'll differ in the way that you construct your graphs. You'll differ in the way you construct your graphs. Even AlphaFold is an example of that uses multimodal graph learning, because at one point they construct this fully connected graph of the sequence that you're trying to, they have a representation of the sequence in which you're trying to predict the structure from. And in order to update the representation of this specific sequence, they take every amino acid and they perform this idea of a triangle multiplicative update. And the reason why they use a triangle multiplicative update is because they want to enforce some sort of the relationship between the amino acids that obey the sort of relationships we expect points in three-dimensional space to have. But the point is that in modifying this update for every amino acid here, based on this idea of like a triangle in a way to encode this inductive bias about three-dimensional space. This is an example of propagating information and modifying this for that. And yeah, I went really fast to the presentation. These are the two like biomedical applications of these of this blueprint that I highlighted in this perspective. And the idea is that if we go back, as I talked about, a lot of these methods, I didn't go through like the whole method because a lot of the ways that they approach these components are very trivial, because multimodal graph learning is still very much in an evolving field, and the idea is that as we go on, we can move on from, for example, right now, as you've seen, most of these graphs that I've described were explicitly given the structure beforehand. But what you can do is you can actually potentially learn the graph structure as you go. For example, for one of the applications that I looked at, which was in particle physics, what you do is that you're trying to use graphs to predict the identity of particles that emerge when two particles hit each other in a particle accelerator. And as you can imagine, as every second that goes by, the relationship between each particles change, because a particle can move and suddenly it's not a neighbor to another particle. So they use the representation of the nodes themselves that represent these particles as a way to build this graph on the fly. So so it's not necessary to give an architecture the structure of the graph to begin with. The hope is that one day you can create this fully multimodal graph architecture where it's an end-to-end, where the model learns the best way to construct this graph, to construct this representation, to do this task of interest. And here I'll go back to the beginning of the talk, where I go over this recently published perspective in Nature, and say that multimodal graph learning is going to become very central as we try to integrate these different data modalities, as I showed examples of before, and will be important for the future. And yeah, that is my talk. Thank you for listening. The paper also comes with a website. I'll briefly stop sharing my screen and show the website really quick. So the idea is that a lot of what I discuss is very depending on your application, you may have a specific way in which you want to use this. You may have a specific way you want to use this blueprint. So the idea is that I created a website where, depending on where we took all the papers that we read, and these are the name of the different methods that I went over. And for each of these components, we explain what is the specific sort of way that they instantiated this component. And the idea is that you can search this depending on your application, but find a specific, if you have an application in mind and you're interested to see how this blueprint was applied to that, you can find the row in the table that corresponds with this, and then see how these different components were instantiated, and then use that for your application or innovate from there. This is a live table, so you can actually, if you're out there and you're working on something and you think it's a multimodal graph learning problem and you want it to be included in this table, because so that other people can look at it and use and see how these different components were used, you can submit that, and this is actually updated weekly. We've gotten quite a few submissions since the publishing of this paper. And the idea here is that, as I talked about, this is an emerging field. And so as more people do multimodal graph learning approaches, this paper will be updated. In fact, recently, here, I'll go back to my slides here. Yeah. Okay. So in fact, recently there's a paper published about trying to trying to generate novel antibodies that use something called equivariant graph neural networks. And the way they actually created this graph to learn on, to generate these antibodies, was using a similar sort of thing as this work here, where instead of modeling the protein like this, they modeled like the nodes represented the amino acids of this antibody, and then you had another graph that represented the antigen that you wanted to bind to, and they use an equivariant graph neural network to then learn what are the amino acids that most likely will bind to the specific antigen. So it's quickly evolving and being used. So yeah, go ahead.
Can I stop you here? Usually, since we're talking about nodes sending messages to each other, so if node representation is in the same space, let's say one image versus another image, so they're sending messages to each other that are already in the same space, right? But the example that you were just showing, so there seems to be like two different types of nodes.
Yes, they're
so they're node features, because when we say messages, we're basically sending the node features over to the neighboring node. So their node features are in two different spaces. Generally, if it is the case, how are they managing to basically send and receive these messages? Because if they are in the same space as AG, you're doing matrix manipulation in the same space. But if they are in different spaces, you have to find some common embedding space to properly process those messages.
Yes, that's a great point. So in these, before you pass the messages, you multiply these node features by some learned weight matrix. So the idea is that this weight matrix you learn will take these node features and move them to a space where then when you do the message passing, it would make more sense. So we don't, and again, these are learned. And the question of like, does this graph here have its own weight matrix, and does this one have a weight matrix? Do they share a weight matrix? These are all design choices that will come as you design. I think this one they use different weight matrices, but then had a specific weight matrix for the passing of the messages across graphs themselves. So they had a within graph and then a cross graph passing. So yeah, and that leads to the third component of the blueprint here, trying to modify standard message passing depending on the topology you have and what you're interested in.
Makes sense. Thank you.
Yeah. But yeah, that is my talk. Thank you for listening. I will take any questions. Yeah.
Yeah, thanks so much, Yasha, for the amazing talk. Before we open the floor for questions, let's all give Yasha a round of virtual applause. And is there any other question from the audience? I can start with a question. Yeah, I find it very interesting, and looks like in the applications you gave the examples, most of the graph are constructed based on or relying on a lot of domain knowledge about the problem and also the data, proteins or small molecules. But you also mentioned that some studies actually learn the graphs on the fly. Yeah, so actually I like the idea of letting the model learn the graph structures, because I feel that by hand designing or constructing the graph, we might miss some. I mean, we never know what is the optimal graph structure for the problem at hand, right? But I also think that the domain knowledge is very important. So I wonder if you have any insights about how to combine domain knowledge with some automatic graph structure learning methods to have graph.
Yeah, that's a great point. There's a lot to say to that, because first off, I think one could perhaps argue that a large language model sort of is doing this sort of thing. It's sort of inherently learning a graph on its own by understanding which connections between which positions to emphasize and which ones to de-emphasize. It's learning graphs and graphs on top of each other. So the thing is, to learn a graph structure, you need a lot of data. And a lot of these applications, they don't have the data on the scales to do something like that, which is why then a lot of these applications are made from domain experts. They come in and they, in creating the graph in the way that they want, they can inject these inductive biases. And then once you do that, these models can learn well without the need to have a lot of data, because we've already given the model a lot of information about the task, and it doesn't need to start from scratch, and it can sort of fill into the architecture we got. So there's an example of changing it on the fly. Well, there are examples of this. For example, in the antibody prediction that for the trying to generate a novel antibody, they will initially give the a structure for the antibody, like in terms of, because we don't know what the antibody is, that's what we want to figure out. So they initialize every like node that represents this antibody versus the antigen as like an empty node. And then as they do it in an autoregressive way, so the first node, they predict what's the amino acid, right? And then once you predict the amino acid of this first node, suddenly the spatial relationship between this node and all the other ones in this antibody changes, because this amino acid has certain properties that will move it in a certain way through space, and you have to reconstruct your graph on the fly. So in this way, the model is sort of like learning a graph, because it'll have to reconstruct the graph at every step. But beyond that, I haven't seen anything like that. And that's why in the Outlook, we've mentioned that this idea of a fully multimodal architecture, where perhaps you can give the models some wiggle room. But also that example I gave, the two small molecules with the graph attention to learn the reaction, that's sort of, you're learning a graph because you're learning what are the connections between the atoms, between these two small molecules that are most relevant for this reaction. And that's not something you're giving the model. You're telling the model to figure that out. So there's a little bit of that there.
Yeah, sounds good. Thanks so much. Any other questions from the audience?
I had a quick question. So amongst all the survey papers that you read, what are some categories of applications that these are used for? Is it mostly on knowledge discovery, or is it like are they looking for more downstream tasks? Like, are they looking for like, I'm curious to, because like there are so many domains, and I'm curious to see how other domains actually like use graph networks for
Yeah, I think knowledge discovery, I think it's mostly used the way I've seen it for like predictive tasks, not really knowledge discovery. Like there's some attribute of some entity that we want to know, and we're trying to use the graph to like predict that attribute. So in the biomedical space, it's like, okay, given a protein and a small molecule, or protein, or a protein or small molecule, like can we predict whether they will interact, what are the properties of each one? In physics, it's given the identity of a mystery particle, can we predict what this particle was based on its momentum and other sort of attributes as it collides? Or, so it's mainly on prediction and not so much discovery, although there are like, explainers. I mean, it's not a presentation on explainability in graph neural networks. I'll let someone else probably talk about that, but I imagine as that field matures and more methods are made there, it isn't crazy to think that you could use it here. For like the small molecule case, there has been like graph neural network explainers used that could show you like what are the subparts of the small molecule it used to make its prediction. And then you could see, oh, is it using a specific motif in the small molecule that should be relevant for this property prediction or something like that. And so in that way, but that is more just like a sanity check rather than like a knowledge like discovery. I don't think we're at knowledge discovery yet.
Got it. And I guess one other question. So I guess in language, like large language modeling, there's like the recent success is you have a really large pre-trained model and then you fine tune on like various applications. Is that trend kind of coming to graph neural networks as well? Like, do you have is it task dependent, or do you have a single model that you can actually like use for various other tasks?
Yeah, I think two answers to that. I think yes, it's definitely coming to graph neural networks. Like I work on a project where we're trying to discover a new type of antibiotic for tuberculosis, and we're using these multimodal graph learning methods to do that. And we found that when we pre-train these graph neural networks with like a self-supervised task and use like a large database of molecules to do this pre-training, which actually improves predictive value. So these sort of concepts are seeping into this field, and I think definitely will be something moving forward. And I also want to say like this paper right here that we talked about like the representations of each of these amino acids in this protein was initialized by the representations learned by a large language model that was released by Facebook called ESM. And they found that when you incorporated the representations of these large language models as the initial representations of these amino acids, your performance improves, your performance actually improves. So that's not directly pre-training, but that's sort of like I guess the knowledge from pre-training started to seep in. So yeah, it's definitely becoming a thing, and it's definitely very exciting.
Cool, thank you.
Yeah, I want to add on that there are actually quite a few works that on self-supervised approaches for graphs, and also there's also like emerging number of like large graph data sets that would allow folks to pre-train a graph neural network. So yeah, I think this field is definitely I mean, like the trend is kind of common in both NLP, computer vision, and also graph learning domains.
Yeah, definitely. That's why the website exists, so that as these things are used more and more, you can look it up and see what people have done without having to read the papers.
One additional question, Yasha. In your survey, did you find many basically sequential graph models, which they would use graph structure for sequential or temporal data? How would you put that into your blueprint?
So I did not see a lot of sequential like time series sort of data used for graph. I think that sorry, I didn't like talk about it, but there are challenges in multimodal graph learning. Like not every application lends itself well to a graph structure. Like it's only if there is an inherent structural component to the problem that you believe is relevant to your task that a graph neural can then leverage. Like a lot of tabular data, you would probably not get any sort of boost from using like a graph neural network. But there have been recently, I know, like I work with Dr. Zitnik, and I think there are some recent works from her group. One postdoc did, I think, a year ago, where I think they use like a graph neural network for time series data. And I could send that to you later. But in this survey, I definitely did not see as much for that, simply for the reason I don't think the graph structure is as apparent there.
Yeah, I think I saw some more papers in the basically traffic modeling domain. So they're trying to, I think, different intersections, there are different nodes, and they're trying to connect those nodes based on, I think, distance, and then traffic flow changes through time. So I think I saw some of the papers. Maybe I'll put it in your website.
Yeah, no, that would, yeah. Feel free to put that in the website. And as I said, we're getting a lot of responses. I update it weekly. And I think with the time series, I guess that idea of initializing the graph, and then as time goes by, maybe the structure of the graph changes as things change, and in this way, in how they do it in particle physics, because I guess that sort of is like time series data, because it's like when the two particles collide, there's time zero, and then as the time goes by, the particles move, and depending on the relative interactions with each other, the particles move in different ways. So one could perhaps make the analogy that it's similar in time series data. So perhaps there's a precedent for doing something like that.
Makes sense.
All right, we can talk more offline because I worked on GNNs for time series data, mostly for like biomedical signals that would have like an underlying graph structure. Yeah. So yeah, Yasha, I'm also excited for the website. So maybe I can submit some relevant papers there.
Yeah. Submit as many as you want. That's why it's there.
Okay. Any other questions? If not, let's thank Yasha again for the amazing talk. Thank you everyone for joining us today. We will upload the recording of the talk to our YouTube channel later today, and hope to see you next time.
Thank you. Thanks again for the opportunity.
Yeah, thanks, Yasha, for joining us today.
All right. Bye, everyone.